All right, let's take a look at electron configuration and electron configuration notation. So electron configuration is the arrangement of electrons in an atom around its nucleus, and this is ruled by three principles. But before we get into those, we have to take a look at how we represent electron configuration notation. So one of the most common ways to represent electron configuration is using an orbital diagram. An orbital diagram is a series of boxes that represent orbitals. Electrons are represented by arrows within each box. This is just an example. Orbital diagrams can be much larger or as small as that single 1s box. And so the 1, remember, is that principal energy level. The S is the sublevel. And then the boxes represent the actual orbitals themselves. And remember, each orbital can only hold 2 electrons. So we represent those electrons using those arrows. And if you watch the animation here, it shows the proper way to fill that orbital diagram. Okay, now we're going to learn the rules that guide chemists when we're writing these and when we're writing electron configuration notation. The Aufbau principle says that each electron occupies the lowest energy orbital available. Ground state electrons always fill orbitals from lowest to highest, and they don't skip any. And remember, ground state atoms are atoms in their normal state. This is actually the orbital filling diagram. And if you start at the top with the 1s and you just follow those diagonals down, it actually gives you the order in which you're supposed to fill those. Okay. The Pauli exclusion principle says that a maximum of 2 electrons can occupy a single atomic orbital, but only if they have opposite spins. So if you look at the top image with the red X, right, in the 2s box, both of those electrons are spinning in the same direction. They have that same m sub s number, that spin number. That can't happen. If they spin the same direction, there's too much charge, and they'll want to spin off to different orbitals. The one on the bottom is correct. You have one spinning up and one spinning down in both of the boxes that have electrons in them. And Hund's rule. Hund's rule just says that single electrons with the same spin must occupy each equal energy orbital before you add extra electrons with opposite spins in those same orbitals. So for example, if you're filling a p orbital, which has 3, right? So your 2p has 3 individual orbitals that can be filled. You have to put in 3 up arrows before you go back in and fill the down arrows. If you look at the image on the right, it shows a correct versus an incorrect filling of those orbitals. So both of these have the same number of electrons. The one on the left has the lowest energy because those up arrows are spread out, those electrons are spread out between the 3 orbitals. And the right side, you've got all 4 of those p electrons smooshed into just 2 of the 3 sets of 3 orbitals that they can occupy. And that actually makes higher energy because when you get electrons, remember, they're all negatively charged. Even though they spin in opposite directions, the charge stays the same. And so if you get too much negative energy in one area, it wants to spread out because there's too much energy repelling them or pushing them apart. There it goes. Okay, so orbital diagrams are a way to graphically represent this. So let's see how we represent it in writing. And that's with electron configuration notation. So your principal energy level is represented by a normal size number, in this case, a 1. Your energy sublevel, orbital types S, P, D, or F, are represented by the letter S, P, D, or F. And then the number of electrons in that sublevel are represented by a superscript 2, or you could say an exponent, okay? So the s orbital can only ever hold 2 electrons. And the sublevel only has the 1 orbital, which is why you hear me say s orbital a lot instead of s sublevel, because they're the same thing. There's only 1. The p sublevel has 3 orbitals. The d sublevel has 5 orbitals. And the f sublevel has 7 orbitals. Okay? And so each one of those orbitals can hold 2 electrons, which means S can only ever hold 2 electrons. P can only ever have 6. D can have up to 10. And F has the most with 14 electrons. So let's do an example of using this. Okay. So we know from the periodic table that a neutral carbon atom has 6 electrons. Okay. You're going to follow the filling sequence until you run out of electrons. And then you're going to check it by adding up the exponents, those little superscript numbers, to make sure they equal the number of electrons in the atoms. So first we're going to do our orbital diagram. We have a 1s, a 2s, and a 2p. You fill the 1s, then the 2s. That's 4 out of the 6 electrons, so we've got 2 left. And then the 2p, you're going to just put in 2 up arrows in those first 2 boxes, right? 1 up arrow, 2 up arrow. Okay, and remember, they're going to separate out into those individual orbitals because that's the lowest energy configuration. Now to write this, which is much shorter than drawing the diagram, you're going to write it as 1s2, 2s2, 2p2. Okay, and if you draw an orbital diagram, you can actually use that to make your electron configuration notation, or you can follow that filling sequence until you run out. So you've got 2 in the 1s, 2 in the 2s, 2 in the 2p. Those match up. Then to check it, we're going to add up those exponents, those 2's. 2 plus 2 plus 2 is 6. It checks 6 electrons. Okay. Now there's another way to think about electron configuration notation, and you can think of it as a roadmap. So we're going to label the periodic table that's in your notes, not the one that's for your labs, but the one that's in your notes, because they're a little different. The rows on the periodic table are your principal energy levels in the notation. So you've got 1, 2, 3, 4, 5, 6, and 7 down that left-hand side. There are 2 exceptions. D block elements, their primary energy or principal energy level is 1 less than the row that they're in, and F is 2 less than the row that they're in. Okay. You can use electron configuration notation and later noble gas notation as a roadmap to find elements on the table, or you can use where they're at on the table to figure out the notations as well. So let me switch back to my cursor. So now you're going to label your sublevels. We call these blocks on the table. Your S block is the first 2 rows on the left-hand side plus helium, just helium. Your P block are the 1, 2, 3, 4, 5, 6 rows on the right, okay, excluding, or columns, goodness, I can't believe I said rows. 6 columns on the right are your P block elements. 2 columns on the left are your S plus helium. Your D block elements are the 10 columns in the middle. And your F block elements are the 2 rows that are pulled out of the table. And so if you look at this table, you've got an asterisk and a double asterisk. And that means that these 2 rows actually go in that space. So the top one will be a 6 and the bottom one is in the 7th row, which means that their principal energy levels are 4 and 5. Okay, that's as high as the F block goes. And if you go back and you look, and I'm going to jump slides for a second. If you go back and you look at this, you can see that your F blocks only have these 4 and 5, right? And then everything else continues on. Okay, let's come back here. Okay. I'm going to leave this up for just a minute. Okay. Now we're going to do an example for noble gas notation. So noble gas notation is a shorthand form of electron configuration notation. To do noble gas notation, the first thing you're going to do is find your element on the periodic table, and we're doing sodium. So you can see it's circled in red. It's the first element in the 3rd row. Now you're going to go to that 2nd row, and you're going to go all the way to the right-handmost column. It's your noble gas. And you're going to find out which noble gas that is. Uh-oh, something didn't go right. And then you're going to start your notation with the element symbol in that bracket. So for sodium, the electron configuration notation is 1s2, 1s2, 2s2, here, 1s2, 2s2, 2p6, 3s1. Okay, so remember the rows are your principal energy levels, and then you've got the blocks labeled. So you can actually use this as like a roadmap. It's like telling somebody to go down to the corner store, but you have to tell them all the steps, right? So like pull out my driveway, go down the road, go to this corner, you'll see the store, go in, get whatever you need, come back out. That's how electron configuration notation works. Noble gas notation is kind of like telling somebody, hey, you know where the Sonic at the end of the road is? Yeah, you're going to turn there. And so to do that, there we go. You're going to find that this guy, your noble gas. And you are going to start there. So you're going to start with that NE in a bracket, and then you're just going to go down to the next row, and you're going to write your electron configuration notation from there. So the NE in the brackets represents all of this electron configuration notation up to the end of the 2p6. So everything from this 1s2 to the 2p6 is represented by that bracket NE, because neon has the electron configuration notation of 1s2, 2s2, 2p6. So that's like telling somebody a shortcut. And it's much easier to write noble gas notation than it is to write out the entire electron configuration notation. Okay, so I'll see you in the next lesson.